Okay, so this is chapter 5, and we're talking about measurement. In this video, we're going to cover section 1 and 2. And so in section 1, some of the objectives that we're going to cover is determine the precision, the accuracy, and the greatest possible error of measurement numbers. We're going to add and subtract measurement numbers and multiply, divide measurement numbers. When we're referring to units, a measurement number usually has units associated with it, and the unit name for that measurement number must be included when you use that number. Write it, or if you talk about it. For example, we know immediately that 20 is a number, 20 feet is a length, 20 pounds is a weight or a force, and 20 seconds is a time interval. Suppose that the length of a piece of pipe is measured to be 8 feet. Two bits of information are given in this measurement: the size of the measurement, which is 8, and the units of measurement, which is feet. The measurement unit compares the size of the quantity being measured to some standard. So if we have an example here, it says if the piece of pipe is measured to be 8 feet in length, it is 8 times the standard 1 foot length. It's important that we address the issue of significant digits. Every measurement instrument and every person making measurements has limitations. Measurement numbers used in technical work and in the trades, have a built-in uncertainty. This uncertainty is not stated explicitly, but is expressed by the number of digits used to communicate the measurement information. Students who are training for technical careers such as engineering will often be expected to round their answers according to an agreed upon rules involving significant digits. The significant digits in a number are those that represent an actual measurement. To determine the number of significant digits in a measurement number, you're going to follow these rules. Rule number 1, digits other than 0 are always significant. Rule number 2, a 0 is significant when it appears between two significant digits, is at the right end of a decimal number, is marked as a significant digit with an overbar. Rule number 3, a 0 is not significant when it is at the right end of a whole number, or is it at the left end of a number. So here's some examples. A tachometer reading of 84.2 RPM has 3 significant digits. All 3 digits in the number are non-zero. That's rule number 1. So we would count the 8, the 4, and the 2 as significant digits. A pressure reading of 3,206 torque has 4 significant digits. The 0 is significant here because it appears between two non-zero digits. So because the 2 and the 6 are on both sides, we're going to count the 0 as significant. A voltage reading of 240 volts has 2 significant digits. The 0 is not a significant digit because it is at the right end of the whole number. So the 2 and the 4 count. The 0 is at the right end, so it does not count. A voltage reading of 240, and you can see the line drawn over the 0 has 3 significant digits. The overbar tells us that the 0 marked is significant. The person making the measurement had an instrument that can measure the nearest unit. A voltage reading 24.0 volts has 3 significant digits because the 0 is significant here because it appears to the right end of the decimal number. A current reading of 0.025 amp has 2 significant digits. The zeros are not significant because they are at the left end of the number. So because measurement numbers are never exact, we need to be careful that the significant digits we specify in the number actually reflect the situation. To work with measurement numbers, we define precision and accuracy as follows. The precision of a measurement number is indicated by the place value of its rightmost significant digit. Okay, so let's read that again. The precision of a measurement number is indicated by the place value of its rightmost significant digit. The accuracy of a measurement number refers to the number of significant digits that it contains. Two different things here. Okay, so state the precision and the accuracy of each of the following measurement numbers using the given rule. Okay, so 4.01, I'm going to kind of make a table here. So let's talk about the precision, and we're going to talk about the accuracy of each one of these things. Well, this is the hundredths place that the 1 is in. And so precision, it says is indicated by the place value of its rightmost significant digit. So it is precise to the 100th second. So we would put 100th second. It has this 0 counts because it's in between two other numbers besides 0. So 1, 2, 3, it has 3 significant digits. Okay. Okay, the 4 is in the tens place, so this is accurate to the 10 seconds. And the 0 is after the 4, and it's to the left of the number, so this only has one significant digit, the 4. Okay, we're going to the leftmost number that's a significant digit, and it's the 1. So this is accurate to this is in the tenths place, so this is accurate to the 10th of a second. And this 0 counts because it's in between two whole numbers besides 0. And this one has 4 significant digits. We talk about the greatest possible error of a measurement. It is defined as half the precision of that measurement. If you are reading the measurement yourself with a measuring tool, the greatest possible error is half the smallest division on the scale of the measuring tool. Here's some examples of that. Suppose the weight of a steel bar is given as 14.6 pounds. The weight of the bar has been measured to the nearest tenth of a pound, so the precision of the measurement is 0.1 pound. The greatest possible error is half the precision, which is 0.1 divided by 2, which is 0.05 pounds. Okay, and you could also do, this would be half of that, so you could take 0.5 and multiply it by 0.1. You would also get your answer at 0.05. So when we talk about the precision here, because we're starting with 14.6 pounds, this measurement is going to be precise to 14.6 plus or minus 0.05 pounds. And what that means is, when you do 14.6 and you consider the plus part, that's going to give you 14.65 pounds. When you consider the subtraction part, 14.6 minus 0.05, you're going to get 14.55 pounds. So this is a tachometer, shows an engine speed to be 4,700 RPMs. The precision of this measurement is 100 RPMs. So the greatest possible error is half of 100 or 50 RPMs. So if we're starting out with 4,700, we want to do plus or minus the 50. When we add, we get 4,700 plus 50. That's what this means, that we're going to add, and we're going to subtract 4,700 minus 50. So that's going to give us 4,750 RPM and 4,650 RPM. So we're pretty sure that our estimate is going to be right between these two values. So on C it says, suppose that you are measuring the lengths of two pieces of tubing with a ruler as shown in the figure. So it looks like, on a ruler, 1, 2, 3, 4, 5, 6, 7, 8. So this actually has the lines that are marked by 8s. So this first line right here would be 2 1/8. Okay, so it looks like that our precision would be up to 1/8. And if you look really close, which is hard to see, this one looks like it's a little bit over 2 1/8. This looks like it's a little bit under 2 1/8. With our human eye, we're going to have a little bit of error there. We're not going to be able to get it perfect. So we're going to take our 1/8, which is what it's marked to, and we're going to divide that by 2, which means 1/8 divided by 2 would be 1/16. And so our measurement is going to be right plus or minus 1/16. So I've got what I think with my human eye is really close to 2 1/8, plus or minus 1/16. Okay, and so when we do 2 1/8 plus 1/16, we are going to get 35/16, which is also 2 3/16. Okay, if we do 2 1/8 minus 1/16, we're going to get 33/16, which is 2 1/16. Very often the technical measurements and numbers shown in drawings and specifications have a tolerance attached so that you will know the precision that's needed. For example, if a dimension on a machine tool is given as 2.835 plus or minus 0.004 inches, this means that the dimension should be 2.835 inches to within 4/1000ths of an inch. In other words, the dimension may be no more than 2.839 inches and no less than 2.831 inches. These are the limits of the size that are allowed or tolerated. When measurement numbers are added or subtracted, the resulting answer cannot be more precise than the least precise measurement number in the calculation. Therefore, use the following rule when adding or subtracting measurement numbers. Always round a sum or difference to agree in precision with the least precise measurement number being added or subtracted. Okay, so if we want to add 4.1, 3.5, 1.27. So this is precise to the tenths place. This is precise to the tenths place because it's our smallest decimal, but this is precise to the hundredths place. So the rule was to always round to the least precise measurement number. So we're going to have to stick with our tenths place whenever we round this number. So 4.1 plus 3.5 plus 1.27. So that gives me 8 0.87, but I'm going to have to round to the least precise number, so I'm going to have to round to the 8. And so my final answer would be, because the 7 is 5 or bigger, 8.9. Okay, so this one is rounded to the tenths place. This one's rounded to the thousandths place. This one's also, when they added them, they just added them the regular way, but because this is rounded, we need the least precise number, which would be the tenths place, so they had to round here, which is going to be 6.7 because the 4 is not 5 or bigger. We've got the hundredths place, the thousandths place, so the hundredths place would be the least precise. So we have to round to the hundredths place. So we're going to stop at the 1. Looks next door. It's not 5 or bigger, so 0.21. It would not round up. 2,473, 321.2. So this is precise to the ones place. This is precise to the tens place. This is the least precise. So we would have to round to the ones place. So they looked next door. It was 2. So they kept it a 4. They did not round up. If some of the numbers to be added are in fraction form, you should convert them to a decimal form before adding them. So the example they've got is 3.2 pounds, 1 3/4 pound, and they changed the 1 3/4 to 1.75 and 2.4. Well, the least precise is going to be our tenths place right here. So they're going to consider the 5 because the 5, so they're going to round to the tenths place. They're going to look next door. There's a 5 next door. So the 3 is going to round up to a 7.4 pounds. When multiplying or dividing measurement numbers, we need to pay special attention to both the proper units and the proper rounding of our final answer. First, let's consider the units. With both addition and subtraction of measurement numbers, the answer to the arithmetic calculation has the same units as the numbers being added or subtracted. That is not true when we multiply or divide measurements. For example, if we want to multiply 3 feet by 2 feet, we're going to do 3 times 2, but we're also going to do feet times feet, which is going to get us 6 feet squared. Okay? When we do this one, we're going to say 2 times 3 times 5 with the numbers, but our units are inches times inches times inches, which is going to be inches cubed. This is 2 times 3 is 6 times 5, so we're going to get 30 inches cubed, 6 feet squared. Okay, so when we're talking about length, it's one-dimensional. When we're talking about area, it's two-dimensional. It's going to be length times height. The units are always going to be squared. When we talk about volume, it's three-dimensional, so it's going to be cubed. Whatever your units are going to be inches times inches times inches, which is going to give you something that is cubed. So to divide 2.4 miles divided by hours, well, you're going to consider the numbers, not 2.4, sorry, 24. So you're going to consider the numbers first. So 24 divided by 1.5, and then you're going to do miles divided by hours. So 24 divided by 1.5 is 16, and then you would write miles over hours, and you would read that 16 miles per hour. And we talked about how the division sign is the same thing as the fraction bar. So both H and HR are acceptable abbreviations for the unit hour. The standard metric abbreviation is H, and HR is in common usage in the United States. When multiplying or dividing quantities, having compound units, it is sometimes possible to cancel or divide out common units. This procedure is identical to the cancellation of common numerical factors when multiplying fractions. When multiplying or dividing quantities having compound units, it is sometimes possible to cancel or divide out common units. This procedure is identical to the cancellation of common numerical factors when multiplying fractions. So to multiply 40 miles per hour times 4 hours, and we talked about this a little bit before when we were in chapter 4, but I would write 45 and then put the miles on the top. Okay, remember, and that happens every hour, so miles per hour, and then times 4 hours, because this really lets you see what happens to the units. Those units are going to cancel out, and so 45 times 4 is going to give you 180 miles. So to divide 45 square yards, okay, so I'm sorry, 42 square yards, you're going to have, and I like to write yards squared like this. You can write square yards either way, but if we're going to divide that, well, that means that the 6 yards would go on the bottom. I really wouldn't have anything on the top because I'm saying 42 divided by 6. But this lets me see that this yard will cancel out one of these yards, and that will leave me with 42 divided by 6, which is 7 yards. When measurement numbers are multiplied or divided, the resulting answer cannot be expressed with greater accuracy than the least accurate measurement number in the calculation. The result of a calculation should not be written to reflect greater accuracy than any number used in that calculation. Always round a product or quotient to the same number of significant digits as the least accurate number in the calculation. So if we multiply 4.35 times 3.6, that's going to get us 15.66, and then we've got feet times feet, which is going to give us feet squared. Now remember, when we round here, the least accurate is going to be the 6, or the least precise is going to be the 6, so we're going to run around to the tenths place. So we would look next door, and since that is 5 or bigger, this is going to become 15.7. Okay, we've got this time it says to divide 375 miles. Now, this could be a little bit tricky, but remember the properties we talked about when we talked about dividing, okay? When you divide, you multiply by the reciprocal. So this is 65, right? Miles over hours. So when we divide, we're multiplying by the reciprocal, so the hours would come on the top, the 65 miles would go to the bottom, which is going to make that cancel out, and we would have 375 hours over 65. So we would actually take those two numbers and divide them, which is going to give us, I'm getting a decimal number, 5.769, it keeps going, and we would have hours. Okay, so the least precise number that we have here, both of them have something to the ones digit. Okay, this one's precise. They're both to the ones place, and so we would want to keep this at the nearest hour. So we would look next door and make that round up to 6 hours. Numbers that result from simple counting should be considered exact. They do not affect the accuracy of the calculation. For example, if a flywheel turns 48 rotations in 1.25 minutes, the speed of the flywheel is calculated 48 divided by 1.25, which is 38.4. We should assume that the 48 is an exact number. Rotations are counted directly, so we express the answer as 38.4 with 3 significance to agree with the 1.25 of the least accurate measurement in the calculation. Each inch of cold rolled steel weighs 0.22 pounds. A certain job calls for 27.5 inches of the steel. How much would this amount weigh? So it says each inch weighs 0.22 pounds, so we would need to take our 22 hundredths of a pound and multiply it by 27.5 inches. Okay, and that is going to be, so it says, I also want to emphasize that this 22.22 pounds is for 1 inch. So it's similar to the problems we were working before where we took it and did this, because our inches would cancel out and we would end up with 6.05 pounds. Okay, and we want to pay attention to what they said. So this was an exact measurement. So they're saying that because we know for sure that this is exact, something that we're counting, like 48 rotations, that we're going to be able to round this one to the hundredths place, so we would be able to keep all of those digits. Some of the measurements made by technical workers in a shop are made in fractions. But on many shop drawings and specifications, the dimensions may be given in decimal form as shown in this figure. Note, the symbol stands for inches. So we've got this 2 quotations, those are inches. If you see 1 quotation, that's feet. So the steel rule used in the shop or any other technical work may be marked in 8ths, 16ths, 32nds, or even 64ths of an inch. A common problem is to rewrite the decimal number to the nearest 32nd or 64th of an inch and to determine how much error is involved in using that fraction number rather than the decimal number. In the drawing shown, find the fraction to the nearest 32nd of an inch, equivalent to 0.462 inches, and then find the error involved in using the fraction number instead of the decimal number. So, to find the fraction to the nearest 32nd of an inch, you would want to take your 0.462 inches times 32 over 32, which is going to give us 14.784 over 32, and this 14.784 is closest to, so approximately, we would round up to 15 over 32. Of an inch. And so to figure out the error involved in using the fraction number, we're going to take 15 minus 14.784 over 32. 15 minus 14.784 gives us 0.216 over 32. So that is 0.00675, and if we round that, we're going to get 0.0068 of an inch error. So change 1.392 into a fraction expressed in 64ths of an inch. So we would do 1.392 inches times 64 over 64. we're going to get 89.088 over 64. In this problem, we're going to round to the nearest whole number, and so that's going to give us 89 over 64, which is good because we know it's more than at 1 inch. And when we find the error, we want to take 1.392 minus 89 over 64, and that's going to get us 0.001375. If we round that, we would get 0.0014 on our error. Okay, so let's get into talking about section 2 on chapter 5. We're going to convert units with U.S. customary within the U.S. customary system. So when you talk about a 4-foot by 8-foot wall panel, a 1 1/4 inch bolt, 3 pounds of solder, or a gallon of paint, you're comparing an object with a standard. The units or standards used in science, technology, or the trades have 2 important characteristics. They are convenient in size and they are standardized. Common units such as a foot, pound, gallon, or hour were originally chosen because they were related either to natural quantities or to body measurements. So in the U.S. customary system, we use several of these units: feet, yards, miles, pints, quarts, gallons, those kind of things. It says consider the following simple unit conversion. Convert 3 yards to feet. So when we start out with this, we're going to start out with 3 yards. But what we want is we want some statement that has yards and feet in it. And whenever I look up here at my table, okay, I know that 1 yard has 3 feet, so I can put the 1 at the bottom, the 3 at the top, and the reason I want the yards to be at the bottom is because I know that my answer is feet, and so I want my yards to cancel out. 3 times 3 would give me 9 feet over 1, and when we divide by 1, that it doesn't do anything to the number. To convert the distance, 4 yards, so we're starting out with 4 yards, to foot units. Okay, we can do that by allowing yards to cancel out. So that means we have to have this unit be feet. So 1 yard is 3 feet, so 4 times 3 is going to give us 12 feet. To convert 44 ounces to pounds, if we know that 1 pound is 16 ounces, we're starting out with 44 ounces. We want the bottom to cancel out, these ounces to cancel out with these ounces. We want the final answer to be in pounds. Then what we want to do is use this statement. So it's 16 ounces. We would put the 16 on the bottom with the ounces over 1 pound. Well, the ounces are going to cancel out, so we would have 44 times 1 over, on the bottom, we would just have the 16. And so to get our final answer, we would do 44 divided by 16, which is going to give us 2.75 pounds. Okay. If you know that 1 rod is 16.5 feet and 1 yard is 3 feet, then convert 11 yards to rods. So we're starting out with yards, and we're ending up with rods as our answer. So we know we're going to have yards cancel out. What statement do we have up here about yards? Well, right now we have 1 yard is 3 feet, so we would put the 1 down with the yard, put the 3 feet at the top. Well, the yards will end up canceling out for us because we've got 1 on the top and 1 on the bottom. But we don't want feet. We want rods. So what do we know about rods? We would have to put feet on the bottom so that it would cancel out. And right now I've got this statement that 16.5 feet are in one rod. Well, now everything is canceled out except for the rod, which is what I need. So to get the answer, I would do 11 times 3 on the top divided by 16.5. Okay, and 11 times 3 divided by 16.5 gets me 2 rods. The average American consumes about 44.7 gallons of soft drinks per year. How many 12 fluid ounce cans would this be? So we've got 44.7 gallons is what we're starting out with. And we want our answer to be in ounces. Okay, so what can we do with this? 44.7 gallons of soft drinks per year. How many 12-ounce fluid cans would this be? Well, we're going to have to look back up at our table to figure out something that's going to change ounces that we know about ounces and gallons. So, and there should be a formula sheet posted under course content that you can find all of these that you can print off. Unit conversions, but this says something about a fluid ounce. That doesn't really help me because it tells me tablespoons. A gallon, oh wait a minute, here we go. 1 gallon has 128 ounces. So that's what I want to use. So 1 gallon, I want to put the gallon on the bottom because we want it to cancel out, has 128 ounces. Okay, so we're going to need to do 44.7 times 128, and on the bottom we would divide by 1, which is it's not going to change the number, so 44.7 times 128 divided by 1, 5,721.6 ounces. The circumference of each tire on a truck is approximately 98 inches, which means that the truck travels 98 inches with every revolution of the tire. How many miles will the truck travel if the wheels make 8,500 revolutions? So we're starting out with 8,500 revolutions. Okay, but what we know is that the circumference of each tire on the truck is approximately 98 inches, so that one revolution, right, is 98 inches. Those are going to cancel out. Now, I want my answer to end up with how many miles? Okay, so need something, it would be nice if I had something that had inches and miles. So let's go up here and look and see what we've got. 1 mile. We know that 1 mile is 5,280 feet. I think I can work with that, right? Because I could change feet to inches. I know that conversion. So let's come back down here. We've got 12 inches in 1 foot. That'll get the inches to cancel out. And we've got 5,280 feet in 1 mile. Okay, so let's look at what we've got to multiply. 8,500 times 98 on the top, because the rest of these numbers are ones, and on the bottom we've got 12 times 5,280. Okay, and remember, it's best to kind of get the top measurement, or what you could do is make sure that you do in parentheses 8,500 times 98 divided by 12 times 5,280 to get our final answer. If you're using your fraction bar and keep all the stuff on the top or the bottom, that would work as well. Okay, this is giving me approximately 13.14 7, and it just keeps going, miles. And if you look at what digits we should round to, we don't have anything that is in the tenths place, so we would actually just say 13 miles on this one. The U.S. customary system of units, the basic units for length, weight, and time are named with a single word or abbreviation: foot, pound, seconds. We often define units for other similar quantities in terms of these. 1 mile is 5,280 feet, 1 ton is 2,000 pounds, etc. We may also define units for more complex quantities using these basic units. For example, the common unit of speed is miles per hour, and it involves both distance, miles, and time, hours, units. Units named using products or quotient of 2 or more simpler units are called compound units. So when we talk about the speed of a car in miles per hour, if a car travels 75 miles at a constant rate of 1.5 hours, it is moving at a speed of 75 divided by 1.5 miles per hour. We write this speed as 50 miles per hour, or 50 mph, and read it as 50 miles per hour. As shown by this example, speed is a component unit because it is the quotient of a distance unit and a time unit. When we talk about area, we know the area is two-dimensional, and we would say 1 foot by 1 foot and get our square feet. Let's use the information to do the following conversion. If I've got 15.25 square feet, how many square inches is that? Well, here's what I know. I know that there are 12 inches in 1 foot. Well, in order for me to know anything about square feet, I'm going to have to square both of these units. This is going to give me 12 times 12, inches times inches. This is going to be 1 times 1, feet times feet. So this would give me 144 inches squared in 1 times 1 feet squared. Well, now I should be able to do this conversion. 5.25 square feet. I don't want square feet, I want square inches. So we want to do our square feet on the bottom, that 1 foot squared has 144 inches squared in it. And we would do 15.25 times 144, and that's going to be 2,196 inches squared, because our feet squares end up canceling out. We also have things that we can do that like some conversions, we just did this one, but when we talk about area units, we've got several conversions here. So suppose we need to convert 4,800 acres, okay, and we want our final answer to be in miles squared, or square miles. And it gives us this fact that 1 square mile is 640 acres. Well, that's exactly what we need. We would put the acres on the bottom. The reason that we would do that is so it would cancel out with the acres on the top, and we would put our 1 square mile on the top. Now we have our miles squared here, and we would just need to do 4,800 divided by 640 to get our answer. 7.5 miles squared. We start talking about volume. Our inches are cubed, or our units are cubed, because we're getting into something that's three-dimensional. So to convert 0.250 cubic feet, so we're starting out with 0.25 I don't need the 0 on the end for the conversion. So feet cubed, and we want to convert it to cubic inches. Let me just, I usually use the exponent and saying, instead of saying cubic feet, I say inches cubed, same difference. But we want to, what do we know? We need our feet cubed to cancel out. We need inches cubed on the top so that our answer is in inches cubed. Okay, and we could do the conversion by hand. We could say, well, what do we know about inches and feet? We know that there are 12 inches in 1 foot. And if we cubed those, because we want to cube the whole thing, not just the inside. So, well, this right here would just turn into 1 foot cubed, but 12 times 12 times 12, is going to be 1,728 inches cubed. And so that's what that would be the statement we need to use. So we would put 1,728 inches cubed. Our feet cubed is going to cancel out. We're going to multiply 1,728 times 0.25, and that gets us 432 inches cubed. Okay, we're looking at our volume units here. It says, you may have noticed that the volume units of a gallon, the fluid ounce, and the pint were all defined earlier as liquid capacity units. Think of liquid capacity as the amount of liquid that a container can hold, as indicated in the table. These units can also be defined in terms of cubic inches, which is the amount of three-dimensional space taken up by each given amount of liquid. For example, a gallon container holds 128 fluid ounces. This is liquid capacity, and the amount of liquid also takes up 231 cubic inches of space. To convert 10,500 cubic inches to bushels, set up the following calculation. So we're starting out with 10,500 inches cubed. Okay, and we want our final answer to be bushels. So let's go up here and look at our table and see if we can find something that has to do with bushels and inches cubed. So right here, there is 2,150.42 cubic inches in 1 bushel. So 2,150.42 inches cubed. And I put that in the bottom because I need those to cancel out in 1 bushel. Okay, so when we do that calculation, we're going to want to divide here because we've got 10,500 bushels on the top, and on the bottom we've got 2,150.42 inches cubed. So when we divide those, we're going to get approximately 4.88. And so we would round that to approximately 5 bushels. Barley has a density of 38.4 pounds per cubic foot. So we're starting out with 38.4 pounds over feet cubed. 1 bushel of barley weighs 48 pounds. And we want our answer to be in yards or cubic yards. So we're starting out with feet cubed. We do know that 1 bushel of barley weighs 48 pounds. And so we're trying to figure out how many bushels of barley there are in 3.25 cubic yards. So how many bushels of barley are contained in 3.25 cubic yards? So we really want, this needs to be bushels per yard cubed. So we need the bottom to be yards cubed. We've done a calculation earlier where we talked about how many feet cubed were in a yard cubed, and we got we know that there are 3 feet per every yard, so 3 times 3 times 3 is going to give us 27 because we're cubing it in 1 yard cubed. Okay, so that's going to get my feet cubes to cancel out. Now I need my pounds to turn into bushels. So we've got to take this taken care of. We need pounds on the bottom and we need bushels on the top. And it says 1 bushel of barley weighs 48 pounds. So 1 bushel is 48 pounds. And that should get us for it because this pounds is going to cancel out with this pounds. So in the end, we would have 38.4 times our 27 over our 48. So it's going to get us 21.6 bushels per yard cubed. Carpenters and workers in the construction trades use a special unit of measure, or volume, to measure the amount of lumber. The volume of lumber is measured in board feet. 1 board foot of lumber is a piece having an area of 1 square foot and a thickness of 1 inch or less. So the number of board feet is equal to the thickness in inches times the width in feet times the length in feet. To find the number of board feet in a piece of lumber, multiply the length in the feet by the width in the feet by the thickness in the inches. A thickness of less than 1 inch should be counted as 1 inch. If the lumber is dressed or finished, use the full size of rough stock dimension to calculate the board feet. So you can see that they've taken their 2 inches here and multiplied it by 12 and then multiplied it by 4 to get 8 board feet or 8 BF. To floor a small building requires 245 boards, each 1.5 inch by 12 inch by 12 foot long. To determine how many board feet should be ordered, well, let's figure out what 1 board foot is. So we would do 1.5 . So we would want to take our 1.5 inches times our 12 inches times our 12 feet. Okay, and so they round this one to the closest inch. So we're going to do 2 inches, and these 2 measurements are both in feet. So 12 inches, there's 12 inches in 1 foot. So we're going to change this to 1 foot times our 12 feet. That's going to give us 24 board feet. Okay, and so we need 245 of those times 24, which is 5,880 board feet. Okay, so let's do a few examples with speed. To convert 55 miles per hour to feet per second, so you want to use 2 conversion factors. You want to use that there's 1 mile in 5,280 feet, or in 1 mile, to convert miles to feet, and that 1 hour is 3,600 seconds. So we're starting out with 55 miles for every 1 hour, and we want to end up with feet per second. So I know I need my miles to cancel out, and I've got this statement that there is in 1 mile 5,280 feet. It's going to get my miles to cancel out. Then I want my hour to turn into seconds, and it says that there is in 1 hour there is 3,600 seconds. So then it's going to make my hours cancel out. So on the top we would have 55 times 5,280. On the bottom we're going to divide by 3,600. Okay. And if we round that to the closest feet per second, we would say 81 feet per second. To convert 3.8 inches per second to feet per minute, okay, we're going to have to think about, let's change inches to feet. Well, we know that there are 12 inches in 1 foot. And then we need to change seconds to minutes. So we know there are 60 seconds in 1 minute. So seconds are going to cancel out, inches are going to cancel out, and we're left with our feet per minute. So we would do 3.8 times 60 over 12. Which is going to get us 19 feet per minute. The 2017 Toyota Camry 4-cylinder hybrid has an EPA fuel economy rating of 40 miles per gallon. The comparable 4-cylinder non-hybrid has an average fuel economy of 27 miles per gallon, but it costs $3,720 less. If gas costs an average of $2.40 per gallon, we can calculate the amount of money the hybrid would save over a 160,000 mile lifespan. So the first thing we're going to look at is that we can go 160,000 miles, okay, in that lifespan. And during that lifespan, if it is the hybrid, we're going to go 40 miles per gallon. So I'm going to put the 40 miles per gallon so I can get the miles to cancel out. And also know that it's costing us $2.40 for every gallon. And we want the gallons to cancel out, so we're going to switch this. So $2.40 for every gallon. So when we take our 160,000 and multiply it by $2.40 divided by the 40 on the bottom, we're getting, because the gallons cancel out, the miles cancel out, we're getting $9,600. This was for the hybrid. Okay, for the non-hybrid, we're still getting a 160,000 miles for the lifespan, but we're only getting 27 miles per gallon. So 1 gallon, it's going to get us 27 miles. And it still costs us $2.40 for our gas for a gallon of gas. So our gallons cancel out, miles cancel out. So we're going to do 160,000 times 2.40, but this time we're dividing by 27. Okay, and that's getting me approximately $14,222 for our, this is the non-hybrid. Okay, but if you'll look back, we paid less for this one. We paid $3,720 less for that one. So just on the gas, if we look at the money we're saving on the gas, $14,222 minus $9,600. We're saving $4,622 just on gas, but when you look at the fact that we paid more for the other one, when you subtract that, ends up being $902. So not a whole lot. And it depends on how much extra energy you were having to put in this hybrid and if it had to have any repairs or anything like that. So $902 for the life of the vehicle. So that is the end of Chapter 5, Section 1 and 2.